We can start or 1 minute more. Busy afternoon in the yeah. So break over can make sense. So 250 250. 10 minutes there. That's 3 to 4. So 45 minutes, 10 minutes break, then 45 minutes. We'll see. Up to you. Yeah. He wants to plan the snacks. Oh, and the snacks. So they have snacks. Okay. You let us know when the snacks are, and we make sure that we stop for the most important part of the afternoon. 250. Yeah, that's priorities enough. Exactly. Okay. Welcome everybody. Thanks for coming. I'm very happy to be here already for a couple of months. Thanks to Arindam, Rahul, and the others here. Today I want to talk a little bit about, I guess, something that are on the one hand basic concepts and computational geometry, but on the other hand hopefully stuff that not everybody already knows now. So maybe let me start by asking, who took a course in computational geometry? Okay. Not everybody, no problem. As I announced, this should be understandable also if you did not take the course. Who of all the terms here, who sort of says for almost all of them, oh yeah, sure. Okay, so Rahul, maybe you take over for now. Okay, so we'll see if I go too fast or too slow, just let me know, right? So the good news is there will be a break, there will be snacks. The bad news is there will be a few exercises. So I'm going to make you work a little bit. Yeah, we'll see. So this is the plan for the coming 3 lectures. So today, Wednesday, and Friday. We'll have to see how fast I go because I didn't really know what the background was. It could be that I have to go a little bit slower or a little bit faster. So it could be that at the end, I'm going to add something or maybe remove something, but we'll see. Okay. And yeah, just stop me at any time when things are not quite clear. Okay, so let me start by briefly motivating the whole area of computational geometry. Right, so I guess, as you know, geometry is everywhere. We live in a 3-dimensional world. So as soon as you want to model, let's say, this lecture hall or anything else, then, okay, you get 3-dimensional data, you get objects in 3-dimensional space. And if you want to compute something, I don't know, let a robot drive around in this room, avoid obstacles and so on, you're dealing with a geometric problem. Okay, and I guess that means that it's clear that for these problems, you want to develop algorithms that can solve whatever you want to do quickly. Okay, so three-dimensional data is obviously there because the world is three-dimensional. Two-dimensional data, if you look at maps, okay, that's two-dimensional data, but also there's a lot of higher dimensional data, right? If you nowadays, let's say machine learning applications, maybe pictures or images are mapped to some points in very high dimensional space, and then you also have some geometric set of points, and you may want to cluster the set of points or things like that. Okay, today I'm going to talk about what is sort of traditionally the case in computational geometry, namely I'm only going to deal with two-dimensional data. So a lot of the things I'm going to tell, they have counterparts in high dimensions, especially three-dimensional data. If you go to really high dimensions, okay, then sometimes the techniques that I will explain now are not really the right techniques, and you may want to do something else. Okay, but for this lecture series, I'm going to talk mainly about two dimensions, sometimes comment on how things generalize to higher dimensions, because in two dimensions, at least I can draw nice pictures to explain what is going on. Okay, and there's also, like I said, geometry is everywhere. Sometimes the data is sort of inherently geometric. Sometimes you don't start with geometric data, but you transform it into a geometric space. Right? What I said about the images, here's another example. If you have a database of employees, they all have an age and a salary, and now you may be interested in queries like, okay, give me everybody, all the employees that are between 30 and 45 of age that earn between 35 and 50K. Okay, that transforms to, given a set of points, right? Every employee is a point with certain age, certain salary, report all the points in the record. Okay, so then what does computational geometry do with these kind of problems? Well, it's a part of algorithm research, of theoretical computer science. So typically we try to come up with algorithms where we can prove that it's always correct. Okay, and if we approximate something, then we want to prove how well our algorithm approximates the optimal solution. And we also want a theoretical analysis of the running time, right? Not only implement it, see whether it works fast in practice, always, most of the time, I don't know, but we really want to have provable mathematical guarantees. Okay, so as an example, suppose I want to compute all intersections in a set of line segments. Okay, what would a computational geometry person do? Say, okay, I have n line segments, I have k intersections. How fast can I compute all intersections in terms of this parameter n and maybe k? Okay, so the obvious thing is for every pair, check if they intersect. Well, we have n segments, so n squared pairs. So this would take n squared time. And can we do better? Well, in general, no, because it could be that all of them intersect. And if you want to report all the intersections, that would take n squared time. But in many cases, in practice, the number of intersections is smaller, let's say only linear. And then there are tools to do that in n log n time. I guess plain Swift algorithm that many of you have seen.
You mean by k intersection?
So k is simply the parameter that is telling me how many of the pairs of segments actually have an intersection. Okay, so that can range from 0 to n choose 2. Okay, oops, one other important comment is that I'm going to ignore in the talk, and that's what we typically do in computational geometry, a number of sort of practical aspects that are important, that are difficult, but that are sort of orthogonal to the algorithmic complexity. Like, okay, that is not that difficult, but given two line segments, how do you actually compute their intersection? Okay, that is maybe not so difficult, but if there are sort of curves defined by some polynomial and so on. So some of these things are difficult. I assume for the rest of the this mini course that whenever you have, let's say, 2 or 3 basic objects like segments or curves or something like that, and you want to answer a basic question, does this point lie above this curve? Is this point inside the circle? All of that you can do in constant time. Okay, it's not always easy to do that, especially since we have typically, you have finite precision. So it might be that because of rounding errors, the algorithm that you had that looked perfectly in theory now crashes. I'm not going to deal with that. I'm going to assume that everything works well, and I'm going to work in the real RAND model. So even if I want to compute the distance between 2 points, which is square root or something, I can just compute it exactly. Okay, the good news is that there is actually an algorithms library that has implemented lots and lots of these basic operations. So if you really want to implement it and you want to make sure that your solution is sort of robust, then using this library is a very good idea. Okay, so there's a lot of things that if you work in computational geometry as a researcher that you must know. So here's a not even very long list. I'm not going to talk about all of that, obviously, because you would need 1 or 2 courses, probably more than 1, to deal with all these things. The people who took the computational geometry course here probably have seen a number of them, but probably not everything, like parametric search, probably very few people in the audience would be very familiar with. I'm going to talk today about randomized incremental construction, and a little bit about Voronoi diagrams, and we will see arrangements later on in the main course. Okay, so I guess that until now, for half of the audience, it was kind of boring because you already knew everything. But still, for the people who are not familiar with the field, I hope this was a useful introduction. Okay, so this is the plan. I'm going to go over these topics, and today probably do the first 2 things: randomized incremental construction and Voronoi diagrams and Delauney triangulations. So let's start with randomized incremental construction. So as a warm-up exercise, let's look at this very simple and very silly algorithm to compute the maximum in an array of numbers. Okay, so here's the algorithm. Obviously, you would do something like, take set the maximum to be the first number, then go over all the other numbers, and when the next number is bigger than the current max, you update the max. But I'm a very paranoid person, so I'm a little bit afraid that this is wrong. So what I do is, if I check if the current number is bigger than my max, then I'm going to check just to be absolutely sure that it's also bigger than all the previous numbers I've seen. But obviously that should be the case if the current max is correct. But just to be on the safe side, let me check this. Okay, and now the question is, okay, obviously that would take more time than just the normal algorithm, but how much worse can it be? So what's the worst case of this algorithm? The worst case running time? N squared, right? Because can I write something? It could be that when I check, what is my index? Oops. Yeah.
Say better to them.
That side is better? Okay. When I check my number I, so It could be that every time I get a new maximum, and every time I have to check all the previous numbers, which would take me something like order number of things I've seen. And this is n squared. Okay, so the worst case is n squared. And yeah, here I simply show how I would test if it's really bigger than all the previous ones. Okay, so that was the worst case, but what this algorithm is doing is it's first putting the elements in random order. Okay. Then the hope is that not every time the next one will be bigger than all the previous ones. Okay, so I start by putting these elements in random order. So I generate a random permutation, uniformly at random. So every permutation has the same probability of being generated. And yeah, let's assume you can do this in linear time. Again, there's some technicalities, as in how can I even generate a random permutation? Do I assume that I can generate a random bit, or do I assume that I can generate a random number between 1 and n? Is it really random or only pseudo-random? Okay, I'm going to ignore that. I'm simply going to say these kind of things using my random number generator from my favorite programming language. I assume it's completely random and that I can do this. Okay. So as we see, the worst case running time was n squared. But what is the expected running time?
N log.
Okay, I hear n log n, I hear linear. Who votes for linear? Who votes for n log n? Okay, let's see. So here's the analysis. So the expected running time is, well, the expectation of all steps, right? I started with linear time for generating the random permutation, and then I have the time for the ith iteration. And by linearity of expectation, I can move the expectation inside the sum. So now the question is, what is the expected time for the ith iteration? Well, if the maximum changes, then I'm looking at all the previous elements to check. So it's the probability that the maximum changes times order I. If I'm lucky, I don't have to do anything, and then I just spend constant time. Okay, so the question is, what is this probability? And the difficult yeah, if I'm unlucky, then at some point I have already generated or picked a set of numbers. Let's say this was x1, x2, x3. Now, whichever number I pick here, it's always going to change the maximum. Okay, so it seems that this probability is maybe quite bad. But why is this maybe better than that? Well, because this is only the case if these were the first three elements. And hopefully the probability of that is small. Right? So there's some hope that this actually works. And so the trick to analyze it, which makes the analysis surprisingly simple, is to use what is called backwards analysis. So the idea is the following. Suppose you look at, okay, I'm adding my elements one by one, and I wonder, okay, what is the probability that the maximum changes when I add an element? I can also think about running the algorithm backwards, and then think about, oh, if I remove an element, so instead of adding the next one, I remove the previous one, what is the probability that the maximum changed? right? So the maximum changes when adding AI to that is the same as saying the maximum changes when removing AI from these first I elements. And then, of course, is if you would pick something randomly, very simple. Like I have my elements A0 up to AI. Okay, one of them is the maximum. Let's assume they're all distinct. And then, yeah, only if that maximum happened to be the last one, only then something changed. Only then the maximum changed. Okay, so therefore with the 0, maybe the I should be I plus 1. But okay, so the probability that this changes is 1 over I, because only if you think backwards, only if the maximum one was the last one that we added, only then the maximum changed. Okay, so this is 1 over I. Okay, so I get 1 over I times order I, so that's 1. So in total here I get order n. There's one subtlety here that I sort of now swept under the rug a little bit, which is that to argue that this is 1 over I need to sort of say, okay, I look at a fixed subset here. Okay, so first I say, it's the subset of the first I elements. So that I fix, but I don't yet tell you what the order was. Okay, but once I fix that, and then I say, well, all the orderings were equally likely. So everybody was equally likely to have been the last one. Okay, then my probability is 1 over I. So this 1 over I is sort of conditioned on that this set are the first I elements. But this 1 over I, well, it actually doesn't depend on what we picked, so it also holds unconditionally. And so it's a little bit subtle, but this is the way it works. So what we've seen now are sort of two aspects of randomized incremental construction that I guess are sort of shown in the most basic version you can think of, namely computing the maximum. One is, okay, what does it do? You shuffle things in random order, and then you add them one by one and update your solution. And 2 is you analyze using this backwards analysis technique. So let's do another example.
Just be pedantic, but that's an equality. It's exactly equal to 1.
Assume distinctness.
Yeah, if the elements are not distinct, then actually if the maximum occurs twice, then even if you pick the maximum, it wouldn't change. So that's why the at most is there.
The way of thinking about this would be that filling the permutation from the back. So creating the permutation, filling entries from A or N. Let's say these two AI plus 1. Something got fixed. Now I have I elements to fill in.
Yeah.
And now
so you could also think about it as, I guess, for many or maybe all incremental algorithms, you can also kind of see them as recursive algorithms, as in, okay, let me first take out the last element, then do something recursively, and now I'm adding the last one. That sort of, yeah, and if you unroll that recursion, you get the incremental version. And in that setting, it's sort of maybe clearer even that, okay, I remove a random element, what is the probability that it was the last one? So in the last step, you would just take constant time. Yeah. Okay. So what is important to note, I guess for most of you, this is sort of trivial, but people get sometimes confused. This uses randomization, right? So I get an expected running time. But the expectation has nothing to do with, oh, I got a good point set that was sort of picked randomly or something like that. For any possible point set, it runs in linear expected time. And the expectation has nothing to do with what the input is, but it has to do with my random shuffling of the input. So sort of, I, as an algorithm, I control the randomness, which is important because sometimes, okay, maybe let me say that later when we get to that part. Okay, so let's do another simple example, sorting. So here's a geometric way of looking at sorting. So I have here 6 numbers. Numbers are points in one-dimensional space, and sorting them essentially means that for every number you want to know what is the next larger one. So that's the same as saying, okay, these numbers partition one-dimensional space in intervals. Like first they have infinite interval from -infinity to x5, then one from x5 to x1, meaning x1 is the next larger of x5, and so on. So if I can compute all these intervals, I've sorted my elements. So now the goal is to compute this set of intervals, and we're going to do that with an incremental algorithm. Right, so we're going to add the points one by one and update the set of intervals after each addition. So here's what we do. My first interval before I have added any points is just from -infinity to +infinity. And then I'm going to add the points one by one. Right, and now I have to find which interval contains my point and then split that into 2 intervals. Okay, so the question is, how do I find this interval quickly? And here's sort of a general way of doing it. General way 1, there will also be a second variant. Number 1 is what is done using so-called conflict lists. Okay, so I simply maintain for every point, every number that I did not add yet, I have a pointer to the interval that contains that point. Okay, then finding that interval is trivial, just follow the point. And also for each interval, I do sort of the reverse. I look at, which intervals all have a pointer to me, so which are contained in my interval, then I maintain a list of those guys. Okay, so here the conflict list of interval I2 would be x4 and x6. Okay, so now it's pretty simple. What do we have to do? Well, I simply use the pointer to go to the interval. I split this interval into 2 subintervals. Now I have to make the conflict lists of these subintervals. Yes. Good that somebody is awake. Yeah, so I have to compute these conflict lists of the new intervals. Okay, if I insert something in the middle of an interval, that means that its conflict list, sort of a number of the points go to one subinterval, the other one goes to the other one. I just look at all the points, see if they have to go left or right. Okay, so that's very simple, and then I have to update all these pointers. Okay, I hope you understand why we need these conflict lists, right? Because I need for each xi, I need a pointer to the right interval, right? That I definitely need. But if I don't have these conflict lists, I don't know for which points I need to update their pointers and so on. Or I would have to look at all the points and see if I have to update their pointers or not. So I need to know which points are influenced, and that's exactly what. Okay, so this is the whole algorithm. Initialization, well, I start with Each point simply has a pointer to this whole big interval from -infinity to +infinity. Okay, what's the worst case running time of this simple sorting algorithm? N squared. Why or how can it happen?
All of them are already sorted.
If you would add them in sorted order, yes. So I start with a whole interval containing everything. Then I add the first point. Okay, I get this interval without anything. All the other points go to the second interval. I'm checking all of them to see if they're here or here. Okay, then I add something. All of them go there. So you get n squared.
These data structure updates here, assuming those primitives to be in unit time.
Hmm?
The data structure primitives, like the update should be assumed to be in unit time, like populating, let's say, ki prime and ki double prime. That's yeah. I'm just wondering the details of that data structure don't matter.
Or it's very simple. It's just this conflict list is just a linear list. So what I have to do, and every point has a pointer to the list of its interval. Okay, so now what this? Okay, I just follow the pointer. I know this is my interval. I know how to split it. Then this is saying, okay, go over the old list for one by one, check, insert it into the list of the left interval or the list of the right interval. Okay, when you insert it in this list, okay, that point gets a point to this one. When it's here, that point gets a pointer to this. So that's all. But there's nothing complicated going on. And all of this is linear in the size of the conflict list that we're splitting. Right? So for every point, we decide does it go left or right in it. So in the worst case, as the example that was suggested, this is linear in how many points we still have left. Right, so it's in the worst case, this is, well, we already, this is the points that are still left. And I split it into something of size 0 and something of size n minus j. The +1 disappears because that was the point that is now added. Okay, so this would be n squared. What happens in expectation? So now I'm going to put the points in random order. We take linear time. And let's see what happens. So we're going to apply backwards analysis. Because again, if you don't think about backwards analysis, you're thinking, oh, it could be that I have one big interval where all the remaining points are, so no matter which one I pick randomly, there's always this huge thing I have to split. Okay, so you should rethink and think going backwards. So this is the current situation. So when is a point, one of my remaining points, when is it involved in the current step? Well, if you should think backwards. So if I remove something, when was that point involved in that step, right? So I remove something. So instead of splitting an interval, I merge two intervals. I remove something gets merged. Everything in that merged thing was involved in that step. Right? If I went forward, then for everybody, I had to decide does it go here or here. So when is a point involved in that? Well, if you look at the interval in the last step, either this was the last point or that was the last point. Right? If this was the last point, then I had been splitting width if this was the last point, I had been splitting this. Okay, so only if you look at an interval and the points in it, or maybe its entire conflict list, then that conflict list was involved in previous step, only if one of the two endpoints was the last one that we added. So that's what you see here. So the total, the expected number of points in the last step is, okay, these are the remaining points. Every point has probability 2 divided by j to be involved in that step, because that point is in one interval, and only if these 2 points, one of these 2 points was the last one, then I have to count that point. Well, there are 2 points, there were j points in total, so the probability is 2 over j. Okay, so I get 2 over j times the number of points, and the +1 is because the point itself that we added, we also have to take into account. Right, and the at most, why is the at most, even if all the points are different?
Points are only like they're the leftmost of the.
Yeah, so this interval points here, they play a role when this is deleted or this is deleted when we think backwards, but I have these half infinite intervals that have only one endpoint. Okay, so if I now sum this quantity, I get, okay, the one is order n, I get this this sum. I hope you see that, okay, if I go from j is 1 to n, if I go in the other direction, I get this, and this is Emily. Yeah, and of course we're sorting, so we shouldn't hope for linear.
It's like interesting to analyze like other like higher order state, like not just the expectation, but things like the variance of
I guess people have looked at that. It's usually not done so much in computational geometry. For sorting, of course, everything has been done what you can think of, kind of. So people definitely looked at these kind of things, and sometimes you need high probability bounds instead of expectation. But by the way, this is essentially the same algorithm as something you already know, which is randomized quicksort. So I'm now going to describe sort of the second way of dealing with or setting up the algorithm. So this was using these conflict lists. So now I'm not going to maintain the conflict list, but do something else. And then it is even closer to randomized quicksort. And the something else is what is called the history graph. So
it's again like the difference between like this probability when we study these randomized stick breaking processes. But this is different because the input itself is deterministic and randomization only comes in through the permutation.
yeah. So now I'm going to change it. I'm not going to maintain conflict lists. So that also means when I add my point, I don't have a pointer to the interval that I need to split. So I somehow have to find that quickly. Okay, here you could imagine you do binary search or something, but I'm going to give you sort of a generic way of doing it, which will also be useful for other algorithms, which is the history graph. So it works as follows. So here we have these intervals that we're computing. Okay, and then we insert something and we delete one we delete one interval and we split it into 2 intervals and so on. I'm going to remember all the intervals that I ever created and build some kind of structure on it, saying that, okay, at some point I had this interval, it was destroyed when I inserted a point, and we created these 2 new intervals. So it's going to look something like this. It's a tree. In this case, in general, it doesn't need to be a tree. It can also be a directed acyclic graph, whose nodes are, in this case, the intervals that I created. So the graph starts with, I have my interval from minus infinity to plus infinity. So this tree starts with one leaf node, which corresponds to that interval. Then I inserted my point x1. Okay, that meant I split this interval into two smaller ones, namely this one and this one. Okay, they become children of this node. Then I inserted, where's my x2? x2, which meant that this one gets split into this one and this one. Then here and so on. And now when I want to find out what is the current interval that contains the next point, so let's say x4, I can walk down in this hierarchy saying, okay, initially it's in here, then out of these two intervals it's here, here it was here, and what it is, x4 is here, so I go here, I have to split this guy. And yeah, so the analysis of that is the same, or actually I should say, you could argue that whatever analysis you do on in the previous framework, you could just say, okay, this cannot be more slower. Why? Well, suppose here with this x4, I'm walking down in this hierarchy, and okay, I have to pay for every interval that I encounter. But so for instance, this x4 is in this interval, and I have to pay for going through this interval. But what did my previous algorithm do? It had the conflict list of this guy. And when I inserted, what is it, x2, I was looking at everybody in the conflict list and saying, do you have to go left or right? Including x4. I was looking at x4 and I was saying, oh, you have to go left or right. So there I also paid sort of cost one for deciding whether x4 goes here or here. I'm just postponing that decision now until I actually search with x4. Okay, is that clear? Good. So the analysis still applies, but we haven't done the analysis yet. So yeah, and then this just says what you have to do now. You search in this history graph, which in this case is a tree, until you get to the leaf. You split the leaf. You create two new subintervals, which now become leaves in the structure. Okay. So I'm not going to give you the analysis of that algorithm. What I'm going to give you now is I'm going to give you an abstract framework that encompasses sorting, but also many other things, and give you a theorem that works in this abstract framework that immediately tells you, not immediately, but almost immediately tells you, oh, now this algorithm runs in this much time. Okay. And I see we have 5 minutes to snacks. So I'm going to sketch, make a start with this, this framework so that you can already think a little bit about it. And then after the break, we will look more closely at how to apply it in different settings. So here's the framework. Okay, so this is, like I told you, it's an abstract framework. So we have a collection of objects. Then these objects define what I call configurations. Okay. What is a configuration? Well, a configuration is sort of generated by some of the objects. But it's also can be in conflict with in conflict with other objects. So it sort of exists if all the defining guys are there, but none of the conflicting guys are there. Okay, and then I can define the active configurations, which are exactly what I just said. Right, so if I look at any subset, okay, we're going to add objects one by one. So at some point I have the first so many objects. What are the configurations I'm interested in? So those are the active configurations. So the defining set should be present, but nothing from the conflict set should be present. Okay, and my goal is to compute all active configurations at the end. Right, so all configurations that are active with respect to the whole set of objects. So for sorting, okay, what are the input objects? Oh. What would be the input objects? What the points? Maybe add minus infinity plus infinity or something. What are the configurations? All intervals, all possible intervals defined by 2 points. One of these points could, or both could be minus infinity or plus infinity. When is something in conflict? Well, if another point lies inside that interval, then it's in conflict with that interval. Okay, so that's sort of the setup. And then the algorithm is going to be very simple, or simple.
Can you go with the construct one more time? So S is like the set of objects. CS is a set of configuration. Again, it's a abstract collection as of now. You're taking any single configuration delta and to define what it like. Can you just explain D delta?
Okay,
Maybe in the sorting example, what is D delta?
I think it will come in a minute. So first, the algorithm is hopefully as expected. Right, I first put my objects in random order. Then I sort of have to initialize. So some of my configurations are active for the empty set. I have to initialize my conflict lists. And then, okay, I'm going to add my objects one by one. Configurations that are currently active but in conflict with the new thing, I have to remove them. Probably new configuration will arise. Right? Like I have this interval, I insert something in that interval that is in conflict with that interval, so I have to remove it. I create two new intervals that become active. And I have to construct the conflict list of these new active configurations. Okay, and again, I have this conflict list for every object. I know, oh, these are the configurations that I'm in conflict with and vice versa. So that's sort of the general thing. And now, oh, okay. Thought it was there, but let's maybe go over your question. Is there a way to wipe the board? This maybe. Okay, and after that, we can almost go for snacks. Okay, so for sorting, I have S is x1 up to xn, union minus infinity, infinity. Okay, this is in my random permutation. Minus infinity and plus infinity must be the first two guys, so it's not quite precise maybe. Then I have, so let's maybe not do this. Okay, so what are the configurations? What is C of S? Okay, that's what you see here. I pick at most 2 points from my set S and maybe something from here that defines an interval. Okay, so each delta in my set CS is such an interval. Okay, so if I have so let's say that this is delta. Now, what is the defining set of delta? Okay, it's simply this. Okay. What is the conflict list or the conflict set or the killing set, if you want to be aggressive? People also call it the killing set. So what is A of delta? Well, that's a set of all xj such that xj lies in delta. Okay, and then indeed, if you look at things that are active with respect to the whole set, okay, I have to look at all my intervals, but as soon as an interval has another point in it, okay, it is not active, so I only get the intervals that are empty, and those were exactly the ones I wanted to compute. Okay, so
And when you said bounded by a constant size, that means this is cardinality is to the delta.
yeah. So that size should be bounded by a constant, otherwise something goes wrong in the analysis. And indeed here, this constant, typically there's a small d that people use or something. In this case, it's 2. Okay, in general, it's we will see some other numbers. And this is the theorem, and then that will be a good point to get snacks. So let me define Sj to be the set, let's say, of the first j items. Okay, so I'm having this random permutation. Sj is the first j items. Then, okay, what is this here? It's the set of active configurations after I add the jth element, minus the active configurations before I added the jth item. Right, so those are the new configurations that appear. So for sorting, what is the number of such things? 2. Right, there's nothing interesting there. In general, it can depend on what is your last element, and it actually is not a fixed number, but it depends on the random permutation and so on. But for sorting, it's simple. It's always 2. You have 2 new things. Okay. What is the expected number of these things? That's this here. And let's see if we can understand that. And that's also where the fact that the number of defining elements is a constant comes in. Okay, so if I want to understand that, what is the technique I'm going to use? Backwards analysis. Okay, so this says how many new configurations do I create when I add something? So now backwards analysis says, suppose I look at what I have now, so I fix Sj. How many configurations do I destroy when I remove something? Okay. when do you destroy a configuration by removing something? Okay. When was a configuration active? Well, first of all, nothing from its conflict list should be present at that time. Well, if I remove something and something it had an empty conflict list here, then definitely that's still the case. So the only way that by removing something you destroy something active is that the other condition is no longer true, namely its defining set is not completely present. So in other words, the last item was in the defining set. Okay, so now I'm saying that the defining set had constant size. That was a condition. And well, I have J elements at the moment. I remove something. So the probability that I pick one of these constant guys things is this. Okay, so the probability that when I remove something that well, an active configuration disappears is that. And so that's the 1 over J. How many active configurations did I have here to start with? Okay. That's simply written here, and that depends on your problem. Right, for sorting, what was the number of active configurations? J, or J plus 1, or I don't know, nothing. Yeah. Okay, so then the number of new things is order 1. Well, we already knew it was 2, so there it's not so interesting. The total size of the conflict list, why is that interesting? Well, because here the way I do it is I have all these conflict lists explicitly. I take my current conflict list. Oh, this is the new guy I add. It has a pointer to this thing. I have to split it and so on. So the time for that is hopefully linear in the size of these conflict lists. So I'm also interested in not just what is the total number of configurations that appear, but also what is the total size of the conflict lists, because that determines the running time. And that is what you see here. And okay, now we know how to analyze the sorting, because the total time was linear in all the conflict lists. This was number of active configurations. Okay, that was just the number of intervals after J insertion. So there was J or J plus 1. So let's put J, then I get N over J. Okay, sum of N over J is N over N. Okay, so I guess we're all anxiously waiting for snacks. So are there any questions at this point? Can you repeat?
In the defining lists overlap.
Yeah, I mean, they do, right? Because here, for instance, if I have these two intervals, this interval is defined by these two, this interval is defined by these two. It can actually be, and we will also see examples of that, that are completely the same. So that a given defining set defines different configurations. We'll see an example of that later on. Okay, and I already kept you away from your snacks for 10 minutes. So let's have snacks and then resume in 10 minutes.
Part 1 controls the update time. Both actually control.
Yeah. So
Part 1 is sort of the size of the.
So if you look at the history graph approach,
Yeah.
then this controls the size of the history graph. Small question. Where are the snacks?
I think next slide has two questions. People want to think about the break.
Hmm?
It says next slide has some questions. People want to think about the.
Okay, so the exercise is, so if instead of, or maybe during eating snacks, you want to think a little bit, come up with algorithms for these two problems. Computing convex hull and computing all into intersection points based on this paradigm. And it's actually not, okay, it's not trivial. Right, so here you would maybe think that, oh, obviously the objects is simply the input, that's always the case. Here maybe my configurations are intersection points and then everything works. That is not the case. So you have to think a little bit more about, the main question is, what are the configurations? And the configuration should sort of tell you what you need to compute. So the configurations for one, if you have the configurations that are active, you should have the convex hull. But you need to define it in such a way that the algorithm can work with it. That's the, yeah, I guess I would be impressed if many people would be able to do that for both of them. Less impressed if they already saw it and simply know it, but yeah. So now, where are the snacks? Outside, excellent.
A copy of your book. It's a signed copy. One of the older editions.
I don't this much, like I use it just feeds the formulation. I use
First of the class that
it's a Duke and UNC that was a program where you don't take classes from your channel. So, Pankaj was reviewing Jack and the offered it.
Usually not, that's good. That's awesome. I see, okay.
So I work with Robert.
I was thinking that somehow in my project was in Vancouver, but after that he was already at UNC. So you work with Herbert, but then you moved into graphics slowly?
No,
or?
I did topology, but in the context of data visualization.
I see.
I did do my PhD in algorithmic with an algorithmic focus on topological descriptors. Then later in my postdoc, I moved to in visualization. Then I continued on both streams, looking at data visualization problems with the topological analysis.
So when did you move to Bangalore?
It's 2006.
Oh,
Yes.
yeah. Are you originally from here?
No, not from Bangalore. I grew up in Chennai.
Okay,
That's in the neighborhood.
yeah. Yeah, well, Dutch standards, it's not.
Yes, I
As for Indian standards, it's
already
just a 5-hour drive or something.
Right.
Yeah.
And I had never been to Bangalore before. Like for me, I did a small internship. When I moved in, it was in the city. But now.
Yeah.
The date? There is second, no, fourth May.
I said to be offered instead of secretary of other thing. And then I would might see some sort of radio regulation. I would go out and some what's happening.
Probably had a mind change, hair or something.
At least have. No, so much of it.
My name is Vijay. BIG. You.
Love me to this club. So, not much that. Then we get good case. So you get this already, I look for those days, it's also very. And I also talk to the, they find company. Hearing about expansion that Anita's company, confidence management company. We talk with that. Now we can talk with that detail about the rate. Yeah, even we get back, I feel interested in it. Yes, I talked to get back, so I'll probably meet her after this interview. Yes. The rates are final because it is 1.6, but the email is repeated 1 email.
They should reduce. Immediately talks from and it first
You know that person.
somewhere in the events they have it was in the air and saying,
we had a little bit of thing earlier. Last time back, like he was not replying to the email, then we it's not now, when he joined that year, 19 or something. So yeah, he was not replying or something. Then I told you know that because wrote an email and then he got rejected to so they without something like this.
we had periods of time. He was super.
Yes,
You know, causing the chair.
no. So you mentioned that last time we not taking like you guys managed to get some money and you are supposed to do something. But then we decided to say, okay, we do later, wait for 2 months. And then he said that, yeah, it's not going to be someone else. But then you don't make it it's not going to be something. So it was wasted and the money was Because they're not doing it required to the kids. It should be like, they're giving us money, but basically the upfront renting Microsoft, and they need like, can we do, you can't be that means. It's not a sentence. Okay, thank you.
Occupationally, I understand. Occupationally, I understand. Just when I believe, but they're not really. So what you need to make it to.
Then, I put it on the requirements, So I don't know, yeah, no, we are profited, if you must not go in this weekend, you get down and you not get the money. Then profitability, we got everything 5 minutes from them. It was going on track. So many emails he wrote, so we would have just done it take 5 minutes rather than writing emails, you will consider, we'll consider. We'll check, we'll get back.
If it reads like if it reads something like a word gift, that's super. They will not accept it.
We are also. They also that.
Yeah, that's the point. That's the point.
They don't want to be answered for parties. Okay, so that's why they can come up. If we already have an MBA, we know why it's already.
They also auditor. The point is, like for example, CSR. They need certain phrases to be included to actually get the tax rate. If you start, yeah.
It's from this left hand side. That's quite confident. That's yes, except for one policy.
You will go over the for the second part.
No,
Okay. J square is slightly mysterious.
yeah, I guess you shouldn't think about it as K squared, but about maybe more as N over J. And so here, okay, the 1 over J, okay, that's clear, and so this is 1 over J times N over J. And it, because otherwise it sort of looks better than the other thing almost, which okay. Let's start again. So okay, we've seen the algorithm, right? It's the abstract algorithm. We're trying to compute configurations that are active. We're adding things one by one. We check or we find out which configurations we have to delete, the ones that are no longer active. Those are the ones that, okay, the new object is in conflict with. Since I have pointers from every object to all the configurations that it's in conflict with, this is easy. Then I have to determine the new configurations, which depending on the problem could be easy or could be difficult. Right, for sorting it, but just splitting the interval into two. And then after I've computed the new active configurations, I have to find their configurations. And hopefully these conflict lists you can compute from the conflict list of the things you destroyed. If you sort of had to do that from scratch, things are not efficient. And then this sort of tells you, okay, this is the total number of configurations. This is the total size of the conflict list. Okay, and for the setting where you maintain this history graph, this determines the size of the history graph. This not determines, but you need this to say something about the running time, right? But well, like I said, you have to determine the new conflict lists. If you're lucky, you can do that in time linear in the size of the old conflict lists, then you get what you want. But that's something that depends on the problem and may not always be clear. So I hope that some of you had some time to think about these problems. This was the framework which we just discussed before the break. So with objects, configurations, defining set, conflict list, this is what you have to define. So what do you think would be the input objects? That's sort of clear, right? That's simply the points. What are the configurations? A suggestion? Yeah, the edges of the convex hull. And I'm going to be a little bit more precise. Well, let's do that later. Okay. If we define them to be the edges, okay, that's what we want to compute. And then, okay, edge has two endpoints, so they define this thing. But when is something in conflict with an edge?
The configuration one edge or the set of edges?
Okay, so each configuration is an edge or a line segment between 2 points. We'll have to modify it a little bit in a second. Right, so the configurations for now are all possible line segments. And I want to find out which of these configurations are actually line segments that are edges of the convex hull. So I should define a conflict set that tells me, oh, if I look at this line segment, it's an edge on the convex hull, if and only if its conflict list is empty.
Line, you have a point that is on both sides of the line. That's a
1.5 be on both sides of the line. If you have points, that's a pairs of points.
It has to be a set of points.
So the negative half space at the.
Oh, I don't.
Yeah, so
suggesting pair of points.
the easiest is, I think, to instead of work with segments, to work with directed segments. So my convex hull is, imagine a clockwise traversal, right? So here, this directed edge is a edge of my convex hull because that's part of my clockwise traversal. So directed segments are my configuration. So I've drawn a few of them. So every pair of points defines 2 of them, right? One from here to here, one from here to here. And then, okay, obviously the endpoints are what defines such a configuration. And here you see an example that a certain subset of 2 points, the same subset defines 2 different configurations. Something in this direction, something in this direction. What is the conflict list? Well, when is that? Why is this directed edge a part of the convex hull? Well, we go clockwise. So if there are points to the left of this directed line, then it's not part of the convex hull. And if that side is completely empty, then it is part of the convex hull. Okay, so for instance, yeah. This edge here. Okay, there are lots of points here, so it's not part of my complex solve. Yeah, and as you can see, this edge, well, there's nothing here, so this one is part of the complex solve. If I direct it in the opposite side, here there are many points, so that one is not part of my clockwise complex solve.
What configurations are like half spaces?
You could also say that they're half spaces, yeah. No, if it's a half space, then it will tap. But yeah, I like to think about it as directed line segments, and then conflict list is that directed line segments defines a half space, and the points in that are the ones you want. Okay, so this was our algorithm. So how would it work? Okay, how do we initialize? Okay, that's a bit annoying. So sometimes it's easier to not initialize with the empty sets, but let's say with the first 2 or 3 elements or something. So that's what I'm going to do now. Right, so here, let's simply work with the first 3. So for instance, these 3. Okay, now I have to initialize the conflict list. So for instance, for this edge, there are all these 3 points. Okay, and I can I have just 3 edges, so in linear time, I can generate all these conflict lists. Now I add the next point. Okay, it's not in any of my conflict lists because it's not here, it's not here, it's not here, so I don't have to do anything. So I go to my next point, let's say this one. This one is in conflict with actually 2 of my configurations. Right? It's to the wrong side of this line, it's in this half space, and it's also to the wrong side of that one.
I think the previous point would be not add a few new configurations. Even though you're not killing anything, but you should still add some edges.
Which one should I add?
When you added the 4th point,
You mean this?
It's not active.
But this is not active, right? I mean, this is potentially a new active configuration because now its defining set is present.
Right.
But we also have elements from its.
are all 6 of them being killed?
Yes, because otherwise it can only be active when it's on the control.
Yeah.
Otherwise, I would have a problem with my whole setup anyway. Yeah. Because intuitively, whenever you have a point inside the convex hull, whatever line you pick, you have a point on either side of it. Okay, so now I have this. 2 configurations are in conflict, so I like this one and that one. Okay, so I have to remove them. And I have to create new configurations. What are the new configurations? Well, simply these 2 things. Right, so here, maybe more generally, a number of edges disappear. This was my convex hull. New point is outside. So all these edges disappear and they get replaced by these 2 new edges. Okay, so here you see that now many configurations can disappear. But we only add 2 in this example.
So part 1 of the theorem controls the second point. And part 2 of the theorem controls, like, cumulatively controls the first. The third statement that you have shown out here.
So part 1 controls
This,
how many edges appear during the.
this is the second bullet here.
Yes.
Second part of the theorem overall is controlled by the overall controls the first bullet.
Yes. Yeah. Because, okay, so here it's only 2, but here you see that it can be many, but overall this is completely fine. Okay. So now what I have to do is I want to create this these 2 new configurations. That's not so difficult because I know which ones disappear, right? I have a pointer to all the disappearing ones. If I know which ones disappear, sort of the last 2, they determine the 2 tangent lines, so I can find that. So that's not the difficult part. But I also have to create the new conflict lists. So what I would like to do is the following. I would like to say, take all the conflict lists of all of these guys. Okay, they are overlapping and so on. So I take their union. And then for each point in union, I decide, is it in conflict with this new edge? And or is it in conflict with that new edge? Is that okay when it comes to the running time? Yes, because the second part of, I'm spending time on, okay, these were all configurations that I created. I take their conflict list, I take their union and so on. That's linear time in this conflict, in all these conflict lists. And yeah, it could be a lot at some point, but overall, here. Right? Overall, if I can bound this, which is the case here, that would be J. Right? That's the active configurations at the size of the conflict hole. That's J after I added J points, or at most J, I should say. Okay, so I get N times J divided by J squared, so N over J, so that would be N log N. Right, and this counts the total size of all the conflict lists that ever appear. So after that, I'm going to remove these configurations so I don't spend time on them later. So here I'm allowed to look at all the points in all the conflict lists. So that seems nice. But there is still an issue. So what is the issue? The issue is not the running time. So apparently the issue must be correctness. So why is this not quite right?
It might be points which are not conflicting earlier, but now are.
Exactly. Right. If I let me draw that example that I had here. Okay. Used to be this. Now I added this point here. This point lies to the wrong side of this line. So it should be in the conflict list, but it's not in the conflict list of this one. Like the ones that are here. Okay, I find all of them by looking at this path plane, this conflict list. But the ones that are here, I don't find. So there's a slight issue. It's not too difficult to see that if it's not in the conflict list of this one, change the picture a little bit, it must be in the conflict list of the previous edge. So I don't have to look at all of these, but I may have to look at this one. So that's nice. I only have to look at one more conflict list on this side, one more conflict list on this side. What is not so nice is that it doesn't fit into the framework anymore, because that particular edge doesn't disappear. So maybe I spend time in this conflict list now, but also later and later and later and later again, because it's always sort of the next edge. So that's a bit of a pity. So what we can do, but let me not spend too much time on it, is I'm going to do slightly more complicated configurations. Namely, a configuration will be a pair of consecutive edges on the complex solve. If you think about it, you could be worried that, okay, now the problem simply, is moved to one edge over, but that doesn't happen. So configurations are now sort of pairs of edges, or this configuration, and then this configuration, and this configuration, and then it fits into the framework. Anyway, so it shows you have to be careful with these things. So in the analysis, number of active configurations, I have j points. So the conflict solve has at most j edges, and at most j of these pairs of edges, maybe. Total running time is linear in the number of disappearing conflict lists. So I get a j here and a j here, and that means that it runs in M-log n time, right? Which is optimal. And it's also pretty simple. I mean, for conflict solve, also the grain scan is very simple. But okay. Yeah, so what should be the configurations if we want to compute all?
For the previous address, will it possible to get some output specific form like cancel with or not?
With this approach, I don't see how. Not really. No. Okay, so what are the configurations here? So we have this framework. Section points would be the natural thing, but somehow that doesn't give you any information. So if I now add, if I just take it section points and I add my new edge, what am I going to do? How do I find based on the what are conflicts? It's a bit weird. So that doesn't quite work. Maybe anyone have another suggestion? What might be more promising is to say, oh, let me, a little bit similar to the 1D sorting thing, let's take sort of these intervals on each line segment between two intersection points or something like that. That's also a bit difficult, doesn't quite work. So what we're going to do is compute something much more complicated, which is the vertical decomposition. So I'm going to say, oops, put a big bounding box around it. And then for every endpoint and every intersection point, I'm going to shoot up and down until I hit another segment or until I hit the bounding box. Right, so that's here. I went up and down and so on. Okay. These regions are all trapezoids or triangles, right? So they have a top side. The top side could be part of a segment, or it could be part of the bounding box. They have a bottom side, again, could be a segment of bounding box, and it has a left side and a right side, which are vertical segments, and they may degenerate into a point. Right? So they could also be triangles. So this is the vertical decomposition. And obviously, so by definition, every intersection point is a vertex of actually several of these trapezoids. But there's a trapezoid here, which is actually a triangle, that one here, here, and so on. So if I can compute all these trapezoids, then I also have all my intersection points. And the nice thing is it's much more complicated, but it also means that it gives us much more information that we can work with. So let's see how it fits into the framework. Okay. Let's do this on the board. Set of objects. Okay, that should be, as always, simply the input. So S is my set of segments. The configurations are all possible trapezoids and triangles that you could ever imagine be arising from these segments. Right, so there's also something where for this vertex, there's maybe this thing here, which you would have if this would be the only segment that is present. Okay, so configurations are all possible trapezoids. Generated by subsets of S, or maybe I should say appearing in the vertical decomposition of any possible subset. Okay.
How large can the set be primarily?
Yes, that was my next question. So if I look at such a trapezoid, okay, what is the smallest number of objects in its defining set? Hmm?
We haven't defined the defining set.
No. So we're now going to the let me draw a picture. So hope you can see. Right, I have a set of segments. This one, maybe this one, and this one. And I look at the vertical decomposition, the trapezoidation, and this is one of my trapezoids. And the defining set are the ones that I really need to define this. Right, so this one, even if this is not there, okay, I still keep the trapezoid, so it's not in the defining set. This doesn't need to be there, but these are there. So in other words, if you look at a trapezoid, we said it had a top that could be part of a segment, or it was part of the top side. If the top side is part of an input segment, then that input segment is in the defining set. Okay, so this is definitely in the defining set. Bottom, well, in this case, the bottom goes to the bounding box, so I don't have anything there. But if I would have this, then this is also in the defining set. Okay, so you need something for the top, something maybe for the bottom. You need something for the to define the left side. So the left side here is okay defined by this. So this one is also in the defining set. And you need something for the right side, which in this case happens to be the same as the top. Right, and in another example, if I do this, okay, I need this for the bottom. I need this one for the top. This one also defines the left. Okay, so it's very, but for this one, I also need this to define. Okay, so it's clear. Is it clear what the defining set is? So what is the smallest possible defining set? The smallest. Oh, I hear one. Does anyone have less than one? I have 0. Right, the whole bounding box. Does anyone have minus 1? No. So the smallest one is 0, right? Just the bounding box, and there's only the empty set defines only one single trapezoid, namely the bounding box. It could be 1, right? So if I have, for instance, in this picture, this trapezoid here has a defining set of size 1. Okay, we can have 2, we can have 3. What's the largest one? Yeah, okay, so you would think maybe, okay, we have the top, we have the bottom. Then for the vertical one, okay, maybe it's an intersection point, so there are 2 more, and then here on this, I also have 2 more because it's an intersection point. But if you think about it, these can never be disjoint. So if I have this intersection point here, then one of them is also defining the top or the bottom. Okay, so if you look at all the cases, it's at most 4. You also see, maybe again, that the same set actually defines a number of different configurations. Like in this case, this, let me, this single segment, okay, it defines this. It also defines something here. And it also defines something here. Also on top. But that's also a constant. Right, so configurations on the trapezoids. Defining set is, well, we've seen it's a size at most 4, so that's good. What's the conflict list? Yeah, and so if you think about, if you look at a subset of our segments, then what we want is that the active trapezoids are exactly the ones that are in the vertical decomposition of that subset. Okay, so first of all, the defining set has to be there. But if another segment of what you have now processed through it, then it will not be in that vertical decomposition. So the conflict list is simply all the segments that pass through that trapezoid. Okay, and then indeed, this is what we want to compute. And as you can see, there's nothing passing through any of these trapezoids. So indeed, the sort of abstract goal corresponds to what we want to compute. And what did our so now things become a bit more tricky. As in, so if I add my segments one by one, I start with no segments. This is my only active configuration, the whole bounding box. I'm adding something. It's in the conflict list of this bounding box. Everybody is in the conflict list of that bounding box, right? Because everybody is intersecting it. Okay, so I delete that trapezoid and I replace it by these 4 new trapezoids. And I have to look at what are the conflict lists of these guys. This is now relatively easy because each of these things is a subset of this bigger trapezoid. So any segment that is in the conflict list, for instance, of this one, was also in the conflict list of this big I. So in this case, it suffices to look at the conflict list of what we had and see for each segment in which conflict list does it go. Okay, so now I add the next one. What happens? It's in conflict with this and this. So I delete these 2 trapezoids. And instead, I create a number of new trapezoids. And I update the conflict lists. What you see always is that when I add something, I destroy a number of trapezoids. That creates a hole in my trapezoidation, and this hole is now filled with new trapezoids. This case, this, and this. Right, so everything here also this used to be longer and so on. And so you get this hole, and you create new trapezoids. That means that everything that is in conflict with one of the new ones was also in conflict with one of the old ones. So hopefully that means we can distribute things quickly. And therefore the whole algorithm with some effort can be made to run in time that depends on the total size of the conflict list that we ever create. So what is the total number of trapezoids that we ever create? That was this theorem saying something like expectation of number of trapezoids in, let's say, the vertical decomposition of the first J segments. How much is this? If you have J segments, then the vertical decomposition is order J. You can prove it using Euler's formula or something. Is that true? I hope at least somebody doesn't believe me. The order J bound.
But J can be quadratic. So the intersection points can be quadratic.
So it's not order J. You have to add the number of intersection points you have at that point. So the vertical decomposition, its complexity is, well, the number of segments plus the number of intersection points, or I should say big O, number of segments plus number of intersection points. Right? If everybody intersects each other, you already have n squared or j squared cells, and then the vertical decomposition will. So this here is order j plus expected number of intersections. Okay, so now I guess being at IISc, you are all very smart people, so you will easily do the rest. But I mean, the expected number of intersections is not very difficult. I mean, of course, it depends on the number of intersections you have eventually. So this algorithm, the running time is going to be something like order n log n plus the total number of intersections. Right? This can be n squared. But then obviously we cannot expect the algorithm to run in n log n time if it has to compute n squared intersections. So it's going to depend on the number of intersections. This step, each step also depends on the number of intersections. So what is the expected number of intersections once we've added the first j things?
2 by choose to make scale.
Yes, I have to parse what you're saying, but it's probably correct. Let me rephrase it or say it in a different way. If you look at any of your intersections of the whole set, what's the probability that it actually shows up among the first j? Okay, this one has to be present and this one has to be present. So that's something like, I mean, probability of this one being present is like 1 over j and this 1 over j minus 1 or something times whatever. So the probability of an intersection showing up is roughly 1 over j squared. So sorry.
J squared.
The probability of, yeah, so it's more like number of intersections. For each intersection, the probability that it shows up is more like j over n for each segment squared, something like that. Yeah. Okay, so, and now if you plug in this number and you do the computation, then you get what you want.
Times the scale, right?
That's here, times number of intersections. That's there, okay. Yeah.
Equal to Okay.
His one was correct. It's like G times J minus 1 by 10.
Yeah. Okay, and if you want to do this with a different algorithm, okay, what does plane sweep give you? It gives you n log n plus k log n. Okay, so this is, if you plug it into the framework and you do the computations, then you get n log n plus k. So it's faster. There exists a pretty complicated plane sweep algorithm, kind of like a plane sweep, but that runs in n log n plus k. It cannot be a real plane sweep, because if you would do the standard plane sweep to compute the intersections, okay, you sweep from left to right, and that means you not only find all the intersections, but you also find them sorted from left to right. And that, okay, this is not a formal proof, but that sort of already indicates that sorting these k things might take you, k log k. So if you really do the standard sweep, it's never going to work. So somehow the sweep should not really sweep from left to right, but be a little bit more careful. So it's sweeping with some kind of line that sometimes you advance here and sometimes you advance here. So the sweep line becomes some kind of curve. And then, okay, there's a very nice paper from the old times, Schinzel Eberbrunner, that shows that you can get n log n plus k. But yeah, this randomized incremental is much simpler. Once you know the framework, it doesn't fall immediately, but fairly easily, I would say. So that's quite nice. And
If we clear about this vertical trapezoid, could have considered other, like, horizontal as well.
yeah, so
Some more even.
I mean, of course, vertical or horizontal decomposition doesn't really matter.
I'm wondering, like, we just like random rotations or some other thing we could. Yeah, I mean, probably the lower bound as well, but.
Yeah, I mean, n log n plus k is a lower bound. So in that sense, there you cannot improve anything. You can also wonder, oh, maybe we can triangulate instead of doing a vertical decomposition, or so you have to ask yourself, what do we need so that it fits into the framework? Okay, so what do we need? First of all, and I did not say that explicitly, although it follows from the definitions, that which configurations are active. If I give you the subset, then it should follow from it's active if and only if the whole defining set is there and nothing from the conflict list is there. In particular, it should not depend on in which order you have added the things. Like you could imagine that you add things one by one, and then so if I arrive at subset 1, 2, 3, I would also arrive there in the order 2, 1, 3 or 3, 2, 1. You could imagine scenarios where what your algorithm is maintaining it after these things is different for 1, 2, 3 and 3, 2, 1. That is not allowed in the framework, because then, okay, it's not that it's present if and only if you have the defining set and nothing from the killing set. It will be present if and only if you have the defining sets and the killing sets, and they are added in this particular order. That doesn't fit into the framework. So that's one thing where you have to be careful when you define the configurations. The defining set should be of constant size, right? That's because if you do the proof with backwards analysis. You say, when does an active configuration, if I remove something, when does it become inactive? Well, if I remove something from the defining set. And if that has size D, and I had J things, that's probability D over J. And then D better be a constant, otherwise things go wrong.
But do you think random rotations help in other cases, like instead of putting selecting the points randomly, if we randomly rotate and then do it in a fixed order, like for example, quick sort, one option is you fix the pivot and take random permutation, other option is you fix the permutation, I mean the ordering and take a random pivot. So both will give you order n log n. So in this case, if we randomly rotate and then do this trapezoidal decomposition, does it help or I mean, in alternate proof or whether it helps with some concentration or anything more for random rotation?
Okay, so here that is not going to work. So if you imagine that the points are on a line, so the vertical decomposition is like that, and suppose you would add them from left to right, then at every step, okay, all the points go to one of the two trapezoids. Let me draw. Okay, so this is my point set. And I insist on adding them in order 1, 2, 3, 4, 5. But we will choose the direction in which we take the decomposition randomly. Okay, so let's first look at what happens if we do it vertically. Okay, I split like this, and I spend time on all the other points to decide if they go here or here. This or like this doesn't really matter. But that is not going to happen.
Like a little bit, this seems like a very nice framework for these dynamic algorithm kind of questions. Like it's already implemented. So this is newer setups where if you have to, you're not given all the points up front, at least diagram, but looks like the one that comes. Yeah, so that's my question.
Yeah, so people looked at this. I mean, to some extent, if you look at it from a worst case perspective, then it's difficult, right? Because what is essential here is that I first do the random permutation, or stated differently, that the points come in random order. In a dynamic setting, okay, people typically assume that an adversary is going to insert points. So people, but if you don't say that, but say that somehow the points are added in random order, then it becomes very close to this. Yeah.
In online random order arrival model, this is what that.
Yeah.
Very fast upgrade then. So you are implicitly maintaining the property that for like the prefixes of the input that you see, you actually maintain a complete right solution. I mean, all of them.
Yeah. Any other?
What other problems have you seen where they applied geometry?
Computing the union of a set of disks, for instance, where you know that the union of disks only has linear complexity. So you don't want to spend time on intersection points between disks that are sort of inside the union, hidden by other disks. So any kind of plane sweep will be difficult. You can do divide and conquer and then a plane sweep that would give you n log squared then, but this will give you n log n. And again, what you would do is, I have set of disks. Again, I compute some kind of vertical decomposition because the union complexity is linear. Also, the number of these trapezoid-like thingies in the complement, that number is linear. Yeah, the defining set is size 4. Conflicts are in exactly the same way. And this, I think, is not even known how to do deterministically in n log n time. Computing, which I will talk about later on, a single cell. So if I have a number of line segments, and I want to compute, I look at the arrangement and I look at the cell, the face that, let's say, contains the origin. So something like this appears in motion planning problems. Then, okay, this doesn't quite work, but there's a variant called lazy randomized construction where you can do this. Linear programming is, it's also randomized incremental and it uses many of the same things, but it's not quite the same framework. But there you also have backwards analysis about when does the solution change and so on. Final question, and then as far as I'm concerned, people can do whatever they want. I mean, you can already do that now, but if you think about this algorithm, okay, we know that the overall number of trapezoids that appear is linear. Well, plus something depending on the number of intersections. Suppose there are no intersections though, just to make the thinking slightly easier. Right, so I have a set of segments. They are disjoint. So collection of disjoint segments. And I want to compute the vertical decomposition. What is the expected number of trapezoids that appear in every step? Okay, so first of all, if I have j segments, then what is the number of trapezoids? That was order j. At the minute, we don't have any intersections anymore. What is the expected number that appears in the when I add something? You can, if you want to cheat, you would say, oh, I know from this theorem that overall it will be n. So probably it's a constant per step, which is true. But using backwards analysis, you could sort of also prove it yourself in a few lines by saying, oh, what is the expected number of trapezoids when I add something? That's the same as the expected number of trapezoids when I remove something. I remove a random element. Okay. What is the probability that if I remove something, that this particular trapezoid disappears? Well, one of its, in this case, two defining objects should disappear. So that probability is at most, okay, in this case, it will be 2 divided by j, but in general, there can maybe be 4 defining objects. So it's 4 divided by j. This is the probability that any particular trapezoid disappears. I have j of them, j times 4 divided by j is order 1. Okay. And I can do it per trapezoid because of the linearity of expectation. Okay, so only. Okay, now the really final question, why on earth would I want to compute this trapezoidation if there are no intersections? Suppose I do it with this history graph approach. Then what do I get at the end? I have the whole history graph. What can I use it for? Point location. So if I have a map, okay, so this is a planar subdivision of a region into a number of faces, and I want to pre-process it for point location. I take the edges of this planar subdivision. I do my randomized incremental construction, just as I had before, except now there are no intersections, but I'm computing all the trapezoids. I get in this, not in the conflict list implementation, but in the history graph implementation, I get all these trapezoids that I ever create in some kind of hierarchy. It's not going to be a tree, but it's actually a DAG. Okay. And then now if I want to do point location, I can use that DAG and I end up in a trapezoid, and that trapezoid also tells me in which region are you. So this is a very nice and simple way to do point location. So it's nice, it's simple. What does not follow from the theory is the expected query time. Because, okay, what it does tell you is that sort of whenever you come with a line segment, you traverse through this hierarchy, and in total that will take you n log n time and so on. So in some sense, it's not really point location, but let's say the point location for the endpoints of these segments, all the trapezoids you traverse through, that is n log n in total. So on average log n. But the theory doesn't tell you much about, now I come with a query point that has nothing to do with the input segments. Can you say anything about how long the path of that point is? Okay, so the answer is yes, but it's not easy. And it was actually open until not, I think people didn't really look at it until some time ago.
Why is the graph no longer a tree?
Okay. Let me do a simple example. This is the first segment. So I start with the root, which was the whole thing. Now I get 1, 2, 3, 4. 1, 2, 3, 4. And now I add, for instance, this one. Okay, so I get what is new, 5, 6, 7, 8, 9. And you can see that, for instance, 7 is a child of 3 and 4. Okay, let's call it a day.
What is the reason for reading of this?
Oh, always this question. First of all, read the book, obviously. Actually, there's another book called Mulmuli's book, something called An Introduction to Computational Geometry through Randomized Algorithms or something along those lines. That is a very heavy book with lots of stuff that I'm explaining. I think probably everything I explained today will be in there. I think this was maybe a bit later. I think that's not in there. But it's a very nice book. It's much more, goes much more in depth than what I did now. And it also, I think, discusses things like how much randomness do you need? Is it enough if you have just one random bit instead of a random number? And if it's not completely uniform, but somehow somewhat only, I don't know, 2 wise independents or whatever these things are called, I have no idea. So it looks at much more complicated scenarios. Yes, I will stop now.
Yeah, let me see, like different asymmetry, since it first part is like a first step guarantee. Like it's saying that every time you're increasing the factor set to an expectation, but if for every iteration way the increment is bounded as such. So the first part is the umbrella theorem that it is. The second part, in contrast, is like a cumulative, right? Like the overall total size of the conflicts is CF4. There's many other applications where even the first part is somewhat relaxed, saying that maybe at some iterations you will see like a large jump, but overall.
I mean, worst case, definitely yes. I mean, we have actually already seen one. Namely, if you do one segment intersection, then when you add the next segment, the number of new trapezoids depends on how many new intersections you create. And that could be a lot and it could be nothing.
Only one case it is. So what is your favorite plan? You can have next time.
Yes.
We were having samosa and kachori. These are not very healthy options, so you could obviously